Hello student to the foundation of classical electrodynamics course. So today we have lecture 15 and we will continue with the curvilinear coordinate system that we started couple of classes ago. We try to understand the different operation, how it looks like in curvilinear coordinate system in generalized way. So today we have class number 15 and doing the same thing, curvilinear coordinate coordinate. I missed one O here. Okay, so today we will try to understand. We already figure out what is how the Laplacian is defined, how the gradient is defined, and how the the divergence is defined. So today we will understand how the curl is defined. So the curl operator in curvilinear system. Okay, curl operator. So we know, again we are going to exploit that expression that this integration, if f is a vector field, and then if I do a surface integral of this quantity, then what we have here, the right hand side, I have a closed line integral, and the line should be such that it encircling the entire surface. So that means if I want to find out the curl of these things, then simply what I do, I need to find out the line integral for a given f. F is same. Let me draw the coordinate system once again, the same old figure. A volume element in scarp space. This is U1, this is U2, this is U3, E1, E2, E3, and this is my origin here, this point O. Okay. So this is the element we are having, volume element we are having here. Now as the way we did in the previous class, we will proceed in the same way, and first we calculate this quantity, that okay, first let me define the f, the vector field, and the vector field f, which is a function of u1, u2, u3, is simply defined as f1 unit vector, f2 unit vector and F3 unit vector. This is my vector field. Okay. Well, so the distance element that we also write here, I am writing once again. So this is d, this distance is ds2 and that value is h2 du2. This distance from here to here is ds1, which is equal to h1 and du1, and finally this length, I should use another color, this length here to here is ds3, which is equal to h3 du3. Okay, this is the length element. Now I calculate this quantity. I calculate curl of f, and maybe I calculate the third component, because this is a vector quantity. So I am just calculating the third component, so that I can exploit the this is the third component. So that means it should be along, so it should be along E3 direction. So I can exploit, if I calculate this, I can exploit this this area, which is in the which is associated with U1 and U2. So that means the area we are having here is this. On the left hand side I have area. So I am making it different notation here, because area is also normally defined with S, but I am making dA1 dA2. Sorry, area should be okay. Area I can simply write in terms of distance, so I don't need to do that actually. So simply I write ds1 distance ds2, that gives me the area. In the right hand side, what we have? In the right hand side I have the this closed line integral. So closed line integral means I need to find out first the surface and then line. So the surface, if I draw here, it should be something like this, a curved surface, and this surface is this one. I am talking about this surface. So here I need to go with the direction as well, because I am calculating the closed line integral. So direction is important, and along this direction, if I find out, so along this direction, this is F2, and along this direction, this is F1, right? Because this is the direction, because this is the direction of E2, and this is the direction of E1 unit vector, and I have the surface element here, where I can calculate the line integral which is encircling the surface, that means the boundary line. Okay. So here already I calculate ds2 and ds1, which is these two. So again I am writing this. So ds2 is h2 du2, and ds1 I calculate here, if you look. So ds1 is H1 d U1. Okay, I am now set. Now I calculate this quantity. Now this quantity I calculate. So first, if I start with this point, then definitely my right hand side I should write, I calculate F1, and then where in this line. So H2 is there, and I need to execute as the point U1 plus DU1, and then I calculate this one, this upper line, which is in the different direction, opposite direction. So I should have F1 and then H2, but I will execute at U1 point, and then multiplied by the length element. Length element H2 I already put here. So the rest part I will going to put, and that is d U2, right, this portion. In a similar way I can do this portion, and here if I calculate the first this one, so that is in the negative direction. So I write F and then H1 F1, because F1 is this direction. Sorry, this should be F2, not F1, because F2 is along this direction. I am making a mistake here. So F2 and F2, but this one will be F1 and F1, and then it should be H1 executing at, oh okay, I am talking about this line. So it is U2 plus dU2 let me check once again. Yeah, this is this line. So this is U2, and then minus F1 H1 executing at U2 point. And then dU1, this is the line. So this if I calculate, then simply it gives me this H1 S1 S2 I put it here. So I can simply get the partial derivative with respect to U1 of F2 H2 and then minus of partial derivative with respect to and then there will be a multiplication of, okay, there will be a multiplication, just a minute, there will be a multiplication of this quantity dU2 and then minus of del U2 and then F1 H1, and that should be in multiplied by dU1. Okay. Now if I calculate the curl of F3, the third component, then it should be 1 divided by ds1 ds2, and whatever I have here, this is this one. I am not writing the entire, so this will put here, and ds1 and ds2 is h1 u1 and h2 u2. So if I put, then this du2 and du1 will cancel out, and eventually I will get this one. Eventually I will get 1 by h1 h2 and then del u1 f2 h2 minus del u2 f1 h1. This is the third component In the similar way, you can find out the first component and second component. In general, if you do all the components and find out, it should look like this. Curl of f in curvilinear coordinate system, or in generalized way, one can write in this way: E1 unit vector divided by h, I think it should be h23. This division what we have, h2 h3, E2 unit vector divided by the scaling parameter 1 3, E3 unit vector divided by the scaling parameter 2 1, and then partial derivative with respect to u1 for this curl operator for form this one and this one, and finally the whatever we have in here, right. So, here we have the field, whatever the field associated with the scaling factor, field component associated with the scaling factor and field component associated with the scaling factor. So, this is the generalized way to write the curl of any coordinate system. You can now put h1, h2, h3 in different coordinate system, because you know what is the value of h1, h2, h3 for Cartesian coordinate system, what is the value of h1, h2, h3 for cylindrical coordinate system and spherical coordinate system. So, you need to use this value to find out what is the curl expression. Now, I am going to write with this note, I am going to write for 3 coordinate system what are the values, just list it. So, number 1 is for Cartesian coordinate system, which is very easy. For Cartesian coordinate, what we have is this. For Cartesian coordinate system, we have h1 is equal to h2 is equal to h3 is equal to 1, because h1, h2, h3 is 1 here. What is the r vector, which is x unit vector I plus y unit vector j plus z unit vector k. Okay. What is d distance vector important, and that is ds I unit vector plus dy j unit vector plus dz k unit vector. H factor is 1, that is why life become very simple here. What is dv? The volume element. The volume element is simply dx, dy and dz. This is the volume element. Okay. Now, what is the operator? Simply, if I have a gradient operator, which is simply I del x phi plus j del phi del y plus k del phi del z. What is the gradient of a scalar field f, which is also very simple? No, this is a scalar quantity, so I should not have I here. It is del f x del x plus del f y del y plus del plus del f del z. Okay. What value of Laplacian we have? What is the expression of Laplacian? The expression of the Laplacian, so this is 2, is this. It is d2 phi dx square plus d2 phi dy square plus d2 phi dz square, and curl simply I j k del x del y del z f x f y f z. So, this is, all these things are well known. So, nothing much to nothing much to remember here, but once you now go for a different coordinate system, that is for cylindrical coordinate system, the next one, 2, we have cylindrical system. In cylindrical system, what we have is h rho. Okay, maybe I can use a different color to distinguish this. So, h rho is 1, h phi is rho, that is a difference here, and h z is 1. R, any position can be represented by rho unit vector plus z unit vector. What is the distance element here, which is d rho unit vector plus rho d phi unit vector plus dz z unit vector. We derived it. What is the volume element here? Volume element, the volume element is rho d phi dz. This is not d rho d phi dz. Rho is here because we have a scaling factor rho sitting here, and in generalized way the volume element, if I write the generalized volume element, then if you may remember, this is H1, H2, H3, and then du1, du2 and du3. Here du1 is d rho, du2 is d phi, and this is dz. H1 is 1, H2 is rho, and this is 1. Now, if I put all these things here, you will find the volume elements, which is this one. Okay. Now, what is the expression of this gradient? The gradient expression is this: rho unit vector del phi del rho plus 1 by rho phi unit vector del phi del rho, and then I have z unit vector del phi del z. Okay. So, that we also derived, and also you can check it with the standard by just putting the scaling factor, and you will get the same result here. Okay. Next, what is the expression of the gradient? The expression of the gradient is this: 1 by rho and then del rho rho f rho, where f rho is the rhoth component of the vector field f. Then 1 by rho and then del f phi d phi, and then I have del f z dz. So, this is the way you can define the divergence in cylindrical coordinate system. And finally, the Laplacian, okay, f, mind it, I should write it here, f is defined in this way. This is f rho, rho unit vector, plus f phi, phi unit vector, plus f z, z unit vector. Okay. So, the next thing that I like to show is the very important Laplacian over a scalar field phi, and it is 1 by rho del rho and then rho del phi del rho. A little bit complicated because two operations are simultaneously doing here, and if you go to the generalized form and try to understand, you will find the result 1 by rho square, next term d2 phi d phi square. Okay, this, okay, I am now in order to distinguish, let us make it big phi here. Let us make big phi here and big phi here, because already we have a phi. And then I have del 2 del z square and a big phi here. Okay. What are the curl elements that also you can find? Let me quickly write this. So, the curl of f in cylindrical coordinate system, mind it, rhoth component, it should be 1 by rho and then del f z and sorry, yeah, 1 by rho del phi and then minus of del f phi del rho, sorry, del z. Okay. What is the component of phi here? This is del f r and then del z and okay, I should not write it r because this is rho, so it should be rho. Rho minus del f z del rho. Okay, and finally this z, this is 1 by rho del rho and then rho f phi minus 1 by rho and del f rho and del phi. A complicated kind of expression you find because you are doing the curl, but at least once you need to know that how it is coming. Maybe it is not that much useful because there are many terms you need to remember, but at least you know that how it is coming, that is the point. Okay. And then finally, I will go for this the cylindrical after cylindrical coordinate system. Finally, I am going in the spherical coordinate system, how these things look like. More complicated thing will be there because the scaling factors are now here. You can see once you have a here the scaling factor is rho, Because of these, you are having all the complicated terms. It is coming in a complicated way because just one scaling factor is not equal to 0. But for cylindrical coordinate system, there are two scaling factor which are not equal to 1, and that is why it creates not problem, but things will be a little bit problematic, complicated in terms of problem. If I say it is problem, that means it is complicated, not so. Spherical coordinate in spherical coordinate, what value we are having? So, we are having h r is equal to 1, h theta is equal to r, and h phi, this is r, and h phi is equal to r of sin theta, that we are having, right. So, the position vector, if I want to express, it should be simply r unit vector. Displacement or distance vector, so this is r dr, r unit vector dr plus r d theta unit vector plus r sin theta phi unit vector, r sin theta phi unit r sin theta d phi, and then phi unit vector. Okay, this is the way we define the distance, these things. What is the volume element? dV is r square sin theta d theta d phi and dr. Again, I like to make you note that in spherical in Cartesian in cylindrical coordinate system, if you have the volume element, it was h1, h2, h3, and then you had du1, du2 and du3. Now, du1 here is dr, du2 here is d theta, d theta, and this is d phi. On the other hand, h1 here is 1, h2 here is r, and h3 here is r sin theta. Now, if you put all this together, you will find that this is nothing but this one, r square sin theta dr d phi d theta. Okay, so now what about the gradient? How the gradient will going to operate in this coordinate system? So, it is simply r, then del r phi. Let us put big phi again, otherwise I will have problems, because here we have a phi variable, and then theta unit vector 1 by r, and then del theta phi, and then I have phi unit vector 1 by r sin theta, and then del phi phi. Okay. So, this is the way one can define the gradient. What about the divergence? A vector field, say A. So, it is 1 divided by r square del r, a complicated kind of things, because of the scaling factor we are having here. 2 scaling factor is not equal to 1, ar plus 1 by r sin theta, and then del theta, and then sin theta a theta, and then finally 1 by r 1 by r sin theta, and this is del a phi del phi. So, I also request you to please kindly check whatever I am writing, maybe there is some error because I am writing. So, please check it from the standard book. A is defined like AR, r unit vector, plus a theta, theta unit vector, plus a phi, phi unit vector. Okay. Now, the most important, Laplacian. How the Laplacian we are going to define here? Laplacian is del square, it is operating on a scalar field f, and the expression is, this is a very important and very useful expression. So, I request you to please remember it at least, r square del r, then r square df dr. Okay. Then I have 1 by r square sin theta del theta. In the argument we have sin theta del f del theta. Okay. And finally, we have 1 by r square sin square theta, and then del 2f del phi square. So, this is a very important expression. In many cases we will find later, and we may need to use that. So, better you should try to remember this expression, or try to understand at least in the context of this curvilinear coordinate system how it is coming. Finally, I like to write the curl expression, and curl of f in cylindrical coordinate system, the r component will be 1 by r sin theta. It is not very useful, because you need to remember, but at least I am writing so that you can understand that how these expressions are there. This is f phi minus del f phi. The generalized calculation is already done in curvilinear coordinate system in terms of the scaling factor. What is here, I am putting the specific scaling factor based on the coordinate system I am using. Theta, this is 1 by r, and then I have 1 by sin theta, and del f r del phi minus del r, then I have r and f phi, and finally I have curl of f phi 1 by r del r, then r f theta, minus del f r del theta. So, these are the complicated kind of expression for the curl of when we are using the cylindrical spherical polar coordinate system. So, I am just write down all the expression for different coordinate system, how the volume element are there, what is the what is the scaling factor, etc., and in general how one can calculate, that is also done in the previous class and this class also. So, I am not going to extend any more. You please practice and you please check the expression from the standard books. Maybe I can make a mistake, there is a possibility, because there are a huge number of expressions I am writing right now. So, there is a possibility that I make a mistake. So, please check yourself by using some standard book, or and then practice few problems where you can calculate the curl when the vector field is given in the spherical polar coordinate system, and you are asked to calculate the curl of that vector field. So, it will be not that easy like you do for Cartesian coordinate system. You need to use these expressions, whatever just written here and whatever is showing is shown now in the in this computer screen. So, today I am going to stop here because I do not have much time. The next class we have the last class, probably I do not know, maybe the last class probably for the module 1, where we discuss about the delta function, which is very important, and we need to understand how the functions, what is the properties of the functions, and how one can use this function in different problems. So, with this note I would like to conclude my class here today. Thank you very much for your attention, and see you in the next class.